Okay. Hello everyone. Good morning or maybe good afternoon. Today, me, Matematika, with my other group and brother, Fajar Fadila and Regina Hana Samsari, will be explain about the materials linear algebra matrix. So, let's go to the topic. Okay. What is a matrix? Matrix is a set of elements organized into rows and columns. And we can see it in the right side. It is column 1, is column 2, and it is column 1, column 2, and it is row 2, row 1, and row 2. A and D are the diagonal elements. B and C are the off-diagonal elements. Matrices are like plain numbers in many ways. They can be added, subtracted, and in some cases multiplied and divided. Nice. Okay, we have two examples of matrix, matrix A and matrix B. Dimension of a matrix, numbers of rows by numbers of columns. The matrix A is a 2 by 2 matrix. B is a 1 by 3 matrix. A matrix with only one column or any one row is called a factor, like matrix B. If a matrix has an equal numbers of rows and columns, it is called a square matrix, like matrix A. Usual notation. Uppercase letters is matrices and lowercase letters is factor. Okay, next. So, matrix, the element. A matrix element is simply a matrix entry. Each element in a matrix is identified by naming the row and column in which it appears. For example, consider matrix D. It is a matrix D with the element 4, 18, minus 20, 14, 5, 4, minus 7, 13, and 22. The element G 2, 1 is the entry in the second row. It is second row and it is the first column. Okay. In the case G 2, 1 is 18. In general, the element in row I and column D of a matrix A is denoted as A, I, G. Next, representing a linear system with matrices. A system of equations can be represented by an augmented matrix. For the example, we have three of equation. Equation 1 is 3x minus 2y equals 4. Equation 2 is x plus 5z equals minus 3. And equation 3 is minus 4x minus 2 plus 3z equals 0. And when to be augmented matrix is like this. It is column for x, it is column for y, it is column for z, and this is the column for constant. It is row for equation 1, and it is column for equation 2, and it is row for equation 3. In a augmented matrix, each row represents one equation in the system, and each column represents a variable x, y, z, or the constant terms. If a variable term is not written in an equation, it means that the coefficient is 0, like this and like this. Okay, next. Matrix row operation, which any two rows. For the example, we switch row 1 to the row 2 or row 2 to the row 1. And this is the matrix. And this is the solution. And the matrix after we switch row 1 and row 2 is like this. Okay, next. Multiply a row by a non-zero constant. For example, perform the row operation 3 times row 2 to be row 2 on the following matrix. And this is the solution. And we can see it. Every element in row 2, we multiply by 3. And this is the result of the matrix. And we can write it like this. Okay, next. Add one row to another. Example, perform the row operation row 1 plus row 2 to be row 2 on the following matrix. And the solution is like this. Okay, let's see a row 2 matrix. Row 1, we edit row 1, edit row 2, and the other element in row 2, edit row 2. And we can say it this, like this, okay. And this is the result. And we can write it like this. It's a simple write. Okay, next. System of equation and matrix row operation. Our Gauss-Jordan method. We have two equations, equation 1, equation 2. Augmented matrix for the equation like this. And we have the symbol, okay, to separate among columns X, column Y, and with columns constant terms. Okay, and the solution we have four steps. Step 1, we change row 2 with row 1 added row 2, and this is the result. The element row 2 to be 0, minus 1, minus 3. And step 2, we change row 1 with a half multiplied to row 1. And this is the element row 1, the result, to be 1, 1, 5. And step 3, we change row 2 with row 2 multiplied row 1. Row 2 multiplied minus 1. And the row 2 become like this, the element 0, 1, minus 13. And the last step, or step 4, is we change row 1 with row 1 subtracted row 2. And this is the result. Notice that the original matrix corresponds to the equation, while the final matrix corresponds to x is 18, y is minus 13, which simply gives the solution. Okay, next. Adding and subtracting matrices. Okay, this subtest have some method, have the same method. Okay, let's see in the bottom side. Okay, a matrix A plus B and matrix C subtracted matrix B. When we are edit or subtracting two matrix or many more, we must to edit or subtracting with the same element. Okay, like this is element A is for its element A 1,1. Edit the element B 1,1. And this is the result of matrix A edit matrix B. Okay, let's see in matrix C subtracted matrix B. Okay, it is the same method, but we have a different sign symbol. Okay, and this is the result of matrix C subtracted matrix B. Okay, next. Multiplying matrices by scalar. When we work with matrices, we refer to real numbers as scalar. The term scalar multiplication refers to the product of a real number and a matrix. In scalar multiplication, each entry in the matrix is multiplied by the given scalar. Okay, for the example, we have a matrix A with the elements 10, 4, 6, and 3. And let's find 2 time matrix A. And we can see it. Every element in matrix A, we multiply it by 2. Okay, like this. You can see it. And after that, it is the result, the matrix, with the element 20, 8, 12, and 6. Okay, next. Okay, from this slide, my friend Fadia Salsabila will be explain it to you guys. So, Fadia Salsabila, it is your turn.
Okay, zero matrices. A zero matrix is a matrix in which all of the entries are zero. Some examples are given below. This is 3 by 3 zero matrix, and it has 3 rows where all the elements are zero, and 3 columns where all the elements are zero. And next example, 2 by 4 zero matrix. It has 2 rows and 4 columns. A zero matrix is indicated by O, like this. O is a 3 by 3 zero matrix, and a subscript can be added to indicate the dimension of the matrix if necessary. Zero matrices play a similar role in operation with matrices as the number zero plays in operation with real numbers. Wait. Okay. In the investigation, a zero matrix behave much like the wait. The real number 0. In particular, we can make the following connection. Add the number 0. Adding 0 to any number gives back that number A. For example, A plus 0 equals A. While at the zero matrix, adding a zero matrix to any matrix A gives back the matrix A. For example, A plus O equals O plus A equals A. At the number 0, adding any number to its opposite will give 0. For example, A plus negative A equals 0. While at the zero matrix, adding any matrix to its opposite will give a zero matrix. For example, A plus negative A equals O. At the number 0, any number times 0 is 0. For example, A times 0 equals 0. While at the zero matrix, scalar multiplication of a matrix by 0 will give a zero matrix. For example, 0 times A equals O. Understanding this connection can help make matrix calculation involving a zero matrix much easier. Okay, notice that the sum of two by 2 matrices is another 2 by 2 matrix. In general, the sum of two m by n matrices is another m by n matrix. This describes the closure property of a matrix addition. If the dimension of two matrices are not the same, the addition is not defined. For example, if I have A is a 2 by 3 matrix and B is a 2 by 3 matrix, and then A plus B is undefined. Why? Because some entries in matrix A will not have corresponding entries in matrix B. Matrix addition and real number addition. Because matrix addition relies heavily on the addition of real numbers, many of the addition properties that we know to be true with real numbers are also true with matrices. In the table, A, B, and C are matrices of equal dimensions. Commutative property of addition. For example, A plus B equals B plus A. Associative property of addition, B plus C and then add the A equals A plus B and then add the C. Additive identity property. For any matrix A, there is a unique matrix O such that A plus O equals A. Additive inverse property. For each A, there is a unique matrix negative A such that A plus negative A equals O. Closure property of addition. For example, A plus B is a matrix of the same dimension as A and B. Okay, for example, associative property of addition. A plus B and then plus C equals B plus C and then add the C. And then add the A. This is the proof. I pick up any numbers for matrix A, B, and C. A, B, and C have the same dimension. And then the result of A plus B and then add the C and B plus C and then add the A is the same. Next, additive inverse property. A plus negative A equals O. For example, if I have matrix A, this is the first rows -2 and 8, the second rows -3 and 1, and then for matrix negative A, the first rows is 2 and -8, and the second rows 3 and -1. If we add A to negative A, we get a zero matrix, which illustrates the additive inverse properties. Okay, notice that a scalar times a 2 by 2 matrix is another 2 by 2 matrix. In general, a scalar multiple of a matrix will be another matrix of the same dimension. This is what is meant by the closure property of scalar multiplication. Properties of matrix scalar multiplication. Because scalar multiplication relies heavily on real number multiplication, many of the multiplication properties that we know to be true with real numbers are also true in scalar multiplication. In the table, A and B are matrices of equal dimension, C and D are scalars, and O is a zero matrix. Associative property of multiplication, for example, C times D and then times A equals D times A and then times C. Distributive properties, C multiplied with by A plus B equals C times A plus C times B. Multiplicative identity property, 1 times A equals A. Multiplicative properties of 0, 0 times A equals O. Closure property of multiplication. C times A is a matrix of the same dimension as A. Okay, for example, multiplicative properties of 0. C times O equals O. For example, I pick up C equals 3. When 3 times 0 matrix, the result is 0 matrix. And next, distributive properties. C multiplied with by A plus B equals C times A plus C times B. Here is an example where C equals 2. And matrix A, the first row is 5 and 2. The second row is 3 and 1. And matrix B, the first row is 3 and 4. And the second row is 2 and 6. And the result is the same. Okay, matrix multiplication. Multiplication of matrices requires a conformability condition. The conformability condition for multiplication is that the column dimension of the lead matrix A must be equal to the row dimension of the like matrix B. If A is an M by N and B an N by P matrix, A has the same number of columns, B has rows. Then we define the product of AB. AB is M by P matrix with its IJTH element. Its element is the sum from G equals 1 to N of AID by JK. What are the dimensions of the vector matrix and result? For example, I have A is 1 by 2 matrix and B is 2 by 3 matrix. And when A times B, the result is C. And C is 1 by 3 matrix like this. Okay, transpose matrix. The transpose of a matrix A is another matrix A with this little superscript T right over here, and also we denote the transpose like this. Created by any one of the following equivalent action. Write the rows or columns of A as the columns or rows of transpose of A. Reflect A by its main diagonal to obtain transpose of A. Formally, the ig element of transpose of A is the gi element of A. Written like this. If I is a m by n matrix and then transpose of A is a n by m matrix. What do I mean about that? Yes, all this mean is rows become columns and the columns become the rows. Okay. If the transpose of A is transposed again, the result is A. Conformability changes unless the matrix is square. For example, if I have A is a 2 by 3 matrix, uh, and then the transpose of matrix A is going to be a 3 by 2 matrix. The two rows here are going to become the two columns. And the three columns here are going to become the three rows. Okay.
Okay, now we have special matrices. On the right side, we have the four similar to scalar 1. Null matrix is one in which all elements are 0, similar to scalar 0. Both are diagonal matrices of diagonal elements are 0. Both are symmetric and examples of idempotent matrices. That is, A equals A transpose and A equals A to the power of 2 equals A to the power of 3 equals etc. Next. Okay, the determinant of a matrix. The first thing we need to know about the determinant of a matrix is that it can calculate only square matrices because it will work only for matrices of the order 1 by 1, 2 by 2, 3 by 3, etc. At this point, we can write the matrix A with A.
Okay, because Regina have a problem with the mix. The determinant of a matrix means the determinant of the matrix A for A 2 by 2 matrix. For A 2 by 2 matrix is half rows and two columns. It is like this. The determinant is A multiply B. subtracted B multiplied C. The determinant of equals or times B minus B times C. It is easy to remember when you think of a course, blue line is positive and red line is negative. Okay, next.
Okay, so it is easy to remember if you think of a cross that has a blue color and red color. The blue color is represent the positive and the red color is represent the negative. Next. Okay, now for a 3 by 3 matrix that has 3 rows, 3 columns, and 9 elements. We can find the determinant keeping the first row as the reference. The first element is A. Now, the element A will be multiplied with the determinant of whatever remains after excluding the first row and the first column. Then, A will be multiplied with the determinant of EFHI. Next, we subtract the first product with B multiplied with determinant of DFGI because B present in the first row and the second column. So after we excluding them, only 4 elements remain, that is DFGI. And to this, we add the product of C with determinant of DEGH. And now we already know how to find the determinant of a 2 by 2 matrix as we told you before. So the determinant will be the determinant of A equals A multiplied by E times E minus F times H minus B multiplied by times E minus F times G plus C multiplied by D times H minus E times G. Next. Now we have inverse of a matrix. Well, for a 2 by 2 matrix, the inverse is going to be equal to 1 over the determinant of the matrix times the adjugate of the matrix. Or in other words, we can say swap the positions of A and D, put negatives in front of B and C, and divide everything by the determinant A times D minus B times C. Next. For a 3 by 3 matrix, or we can say elementary row operations. The elementary row operations play around with the rows, such as adding, multiplying, or swapping, until we make matrix A into the identity matrix I. And by also doing the change to an identity matrix, it magically turns into the inverse. The elementary row operations are simple things like adding rows, multiplying, and swapping. Example, find the inverse of A. First, we need to rewrite this in the form of an augmented matrix with matrix A and the multiplicative identity of a 3 by 3 matrix. Next. Now, we do our best to turn A, the matrix on the left, into an identity matrix. The goal is to make matrix A have ones on the diagonal and zeros elsewhere, or an identity matrix. And the right-hand side comes along for the right, with every operation being done on it as well. But we can only do these elementary row operations with swap rows, multiply or divide each element in a row by a constant, replace a row by adding or subtracting a multiple of another row to it, and we must do it to the whole row, like this. Okay, so after we start with A next to I, then we divide row 1 by 5, and then we add row 2 to row 1, and then we take 2 times the first row and subtract it from the second row. After that, we multiply second row by minus a half, and now we swap the second and third row, And for the last, subtract the third row from the second row. Matrix A has been made into an identity matrix, and at the same time, an identity matrix got made into A inverse. So we get the A inverse equals 0 0.2, 0 0.2, 0, minus 0 0.2, 0 0.3, 1, 0 0.2, minus 0 0.3, and 0. Okay, so there are the explanation that my friends and I told you about the linear algebra matrix. Now it's time to do some quizzes. If any of you already find the answer, please unmute your microphone and tell us what the correct answer.
May I try?
Yes, please.
The number one, the answer is the first row is 6 and 16. The second row is 16. The second row is 16 and 8.
Yes, your answer.
Yes,
Sita, can you repeat your answer?
the answer. The first row is 6 and 16. The second row is 16 and 8.
Yes, correct. Okay, so anybody wanna try? Number two and number three?
Okay, anybody want to answer number 2 and number 3?
May I answer? Number 2.
Sure.
Yes, please.
The answer for the first row are 17 and 8, and the second rows are 8 and 4.
Yes, your answer is correct.
Can I try number 3?
Yes, please.
The answer is minus 306.
Yes.
Yes, the answer is correct.
Okay, thank you.
Okay, so here is the key answer to the question before. And now we're already at the last page of our presentation. If anyone has any question, please feel free to ask now, and we will try our best to answer.
Can I ask the question?
Yes, please.
Uh, Before I ask, thank you for your presentation. It's good presentation. In your slide, you cannot you not included definition and a concept about trace of matrix a trace of some matrix trace. Can you give explanation about trace of matrix and give me an example about trace of matrix? Thank you.
Okay, this is the trace matrix. Trace matrix is a square matrix A with n by n columns and rows, and we definition it with the sum of the main main of element diagonal in matrix A, and this is the notation like this. And this is for the example. We have a matrix A with the element minus 1, 2, 0, 1, 2, minus 2, minus 1, 1, 3. And this is the trace matrix for A. It is an element matrix A 1, comma 1. Edit the element matrix A 2, comma 2. And edit with the element matrix A 3, comma 3, comma 3. And this is the result. It's 4. Okay. Okay.
Okay. enough. Thank you.
You're welcome.
Anybody want to ask again? Okay, if there are nobody want to ask again, we will close this presentation. But before that, can you guys please turn your camera on because we will get the documentation. Okay, so now I can see that our time is just about up. So to finish this presentation, we would like to say thank you for all of you that pays attention to our group presentation. And I hope our presentation will help you to be more understand about metrics. We are sorry if there are any mistakes in our behavior or the way we talk during our presentation. Have a nice day and wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.